So now we're going to talk about the number one way that interference actually occurs, and that's through path difference. Now, path difference actually causes a phase shift. So go ahead and burn that in your head. A path difference causes a phase shift. Path difference is whenever one wave starts before or after another wave. So one has to go a further distance than the other. Now, path difference of one or more whole wavelengths gives you no phase shift, and it's going to give you constructive interference. So let me show that here on this little drawing up here. I have two waves, one in red and one in blue. So there's the red, here's the blue. And whenever there is no path difference, they both start from the exact same place. Obviously, you have constructive interference. You can see how everything lines up. What happens, though, if I start the blue wave one whole wavelength in advance? So I'm going to slide this blue wave now to where it gets a whole wavelength in advance, and then it's not exactly perfect because my drawing isn't exactly perfect. But if I slide it there, I go up, I go down, and then I'm back starting over again. A entire wavelength in advance gives me constructive interference again because it gives me a phase shift of 2 pi. And anything 2 pi, 4 pi, 6 pi, so forth, so on, actually gives me no phase shift in the end. And likewise, if I continue to slide it, right, I would continue to get, like, here's a path difference of 2 whole wavelengths, or in our terms here, n lambda, some whole number times lambda. Anytime you start a wave a whole wavelength ahead of another wave, assuming that these are identical waves, we're going to get to terms monochromatic, we're going to get to terms coherent, but assuming that one wave is starting, that there are two waves are the same, if one wave starts a whole wavelength or 2 whole wavelengths in advance of another, you're going to get constructive interference. Now, and given by the equation n times lambda, where n is any whole number. So if you have a path difference, or one starts ahead of the other, 1 wavelength, 2 wavelengths, 3 wavelengths, constructive interference. Now, destructive interference means you need half wavelengths. So for example, what if I took my blue wave and I pulled it over where it started 1/2 wavelength. So it goes up, that's only half of a wave. The blue wave is starting half a wavelength in advance, and then it comes back down. Notice those are perfectly out of phase. You're going to get destructive interference, or pi out of phase, a pi phase shift. So a path difference of half wavelengths leads to a pi phase shift, aka destructive interference. So what we can say here is destructive interference occurs at any whole number plus a half. That way we always end up with some half number right here times your wavelength. So this would be a 0 for n, right? And then if I continue to slide it over, right, there's a hole, so I got to keep sliding. Now I'm back to 1.5, right? So n would be 1 plus a half, 1.5 times the wavelength. Started 1.5 wavelengths, meaning you can see 1.5 wavelengths there in advance. Once again, I get destructive interference. So anytime you have whole wavelengths in advance, or whole wavelength path differences, you get constructive interference. Anytime you have half wavelength path differences, you get destructive interference. Now, if what I just said was very confusing to you, you might need to do 2 things. First, you might need to go back to the video on phase difference and go back over that, and back to the video over constructive and destructive interference to get that idea burned into your head. Then come back and rewatch this slide on the video to think about path difference and how that affects phase difference to give you constructive and destructive interference. All right, so now let's look at how path difference can actually occur. I have over on this side a block, if you will, something that's going to block light with 2 very small slits in it, separated by distance b. So 2 very small slits, and b is actually very, very small, generally on the order of micrometers, you know, maybe tens, maybe hundreds of micrometers. So very, very small distance between, and I have monochromatic coherent light. Now let me talk about that for a second over here. Monochromatic means 1 wavelength, which we associate with color. Reason that's important is because wavelength actually plays into the equation. I'll talk about how whenever light passes through a slit, you actually get different diffraction patterns for interference patterns for different light colors, but we'll talk about that later. And coherent means it's initially in phase. In other words, this is all the exact same light coming in, identical to each other. There's not mixtures lasers and everything else coming in, and it hits two small slits. Now these two small slits end up becoming their own point sources. In fact, on the previous slide, you saw a little picture of that idea. So they become their 2 point sources, and those 2 point sources, brand new point sources, will interfere with each other. Remember the idea of basic diffraction. So then these 2 point sources will end up interfering with each other. Now, the difference to any spot on here, there's a path difference to any spot on, let's say, a screen on this side. Now, whenever you look at, if you put a screen over here, you would see what we call an interference pattern, a bright spot, a dark spot, and then a little bit dimmer bright spot, and then a dark spot, and then a little bit dimmer bright spot, and the same thing going down below. And the reason for that is there is a path difference, because the distance that the wave has to travel from this point is shorter than the distance that it has to travel from that point. Now, for constructive interference to occur, we said that the path difference must be some n lambda. In other words, this one travels, let's say, L, for example. Here we go. L. Then this path right here, the bottom one, right here, must be L plus n lambda, where n is some whole number, to get constructive interference. Notice the path difference in lambda. So if I call this section of it right here L, that leaves this little portion right here in the beginning to be n lambda. Now, here's an angle right here. This would be a right angle, and the reason I can assume that's a right angle is D, or the distance from here to the screen, is much, much larger than B. This is on the order of micrometers, maybe millimeters, right? And the screen is in the order of meters. So we're talking times 10 to the third generally, or bigger than that, further distance away. So at that point in time, this actually becomes a right triangle right here. Now I'm going to pull this triangle out and zoom it in, if you will, right here, because it's somewhat difficult to see. Here's my right angle. The assumption here is if B is so much larger, if D is so much larger than B, these two lines are almost parallel, making this a right angle. Here's the hypotenuse, B, of this triangle. The hypotenuse is always opposite of your largest angle, which is the 90-degree angle here, so always opposite the 90-degree angle. Here's the base, if you will, n times lambda, and then you have some theta right here that we're talking about, and I'll get to why that theta is important here in a minute. So here's an equation that I can write just from this basic triangle that comes from here, relating my path difference for constructive interference. Any constructive interference spot will always occur whenever this angle, sine theta, opposite over hypotenuse, sine theta equals my opposite, n lambda, over hypotenuse b. So sine theta equals n lambda, where n is some whole number, 1, 2, 3, representing which bright spot you have, like I said, mirrored top and bottom there, times the wavelength of light divided by the distance between the two slits. Now, small angle approximations are a very useful idea. If you are in radians, then as long as you are below 14 degrees, sine theta is just about theta, so we can actually drop the theta of sine theta and just turn that into theta here, because we have to assume that this angle here is going to be very, very small. Reason that we can assume that is B is so much smaller than D. D is a long, long ways away. Tangent, which we're going to use next, small angle approximation, your theta must be less than 10 degrees, and do take note that these angles are in radians here for that to work. And we're actually going to have to go with the tangent, because we're going to use tangent here on the next slide. So you need to make sure that your angles are all less than 10 degrees, and I'll translate that into radians here in a moment. All right, so I went ahead and translated this into radians for you. We're talking 0.244 radians is about 14 degrees, and 0.176 radians is about 10 degrees. So make sure your angles are less, because we're going to use tangent here also. 0.176. Now, you might have been thinking on the last slide, where on earth is Mr. Birch going with all of that? Where does this little angle with this path difference and this odd concept relate to what you can actually physically see as an interference pattern? Bright spots, also called maximas, right? This would be a zero order maxima, first order, second order maxima. Here's another first order, second order, coming away from the center line, which is your zero order maxima. And then destructive spots called minimas coming down like this. Lots of times this will be labeled first order here, second order, minimas coming down like that. How does this angle right here and this little triangle dealing with this little path difference, because it goes a little bit further, relate to this screen? Here's how. Whenever D is much, much further, the distance to the screen is much, much larger than B, then if you draw a triangle starting from the very center between the two slits up, here's a nice little right triangle going over to the central maxima, aka the zero order maxima, height coming up to a first order, or you could go up to a second order, whichever you prefer, whichever bright spot you're dealing with. So just nice little right triangle here. The angle of that triangle is actually the same angle as this little triangle here. I'm not going to go through the proof of that now. I might do that later for you. Now from this triangle, we can write another equation. Tangent theta, here's my theta, tangent theta equals opposite h over adjacent d. Now, h and d are two very, very easy measurements to take. You can get out a meter stick. H will generally be in centimeters, right, which your meter stick measures. D lots of times will be in meters, which your meter sticks measure. So you measure these two quantities, h and d, very easily just using a standard meter stick. That allows you to calculate this angle here. Now, with that, you can then carry this angle, right, that it was coming up to, the angle that it rose up to the maxima spot, over into this equation here. Which order are you dealing with? In other words, what number? Here's a zero order, first order maxima, second order maxima, dealing with constructive interference. Which one are you dealing with? Wavelength of light and B. So if you have a machine slit where you actually know the distance between the two slits, because that's going to be too small for you to measure with a meter stick easily, but if you actually have a machine slit where you know the distance between them, you can very, very accurately calculate the wavelength of light. I'm going to move quickly on these next two slides. Now we're switching to destructive interference, which means we have a path difference that's always half wavelengths, n plus 1/2 lambda, although lots of times if we're calling this first order minima, this second order minima, and then so on, right, the destructive, the dark spots, this plus would actually need to be changed to a minus. It still gives me half a wavelength difference. If someone's trying to call these zero orders and then counting up from there, 0, 1, 2, then you would need the plus. But normally, you're going to end up needing this to be a minus sign here because they'll call these first, so forth, so on. So same exact triangle that we were dealing with earlier, right? Path difference here. This one goes further than that one to the minima spot to get perfectly destructive interference, a complete dark spot, monochromatic, coherent light, or any source of a wave. It could be sound waves. It could be anything. You're going to need a n plus, or we're using n minus now. Make sure to change that equation there. N minus 1/2 lambda divided by b, where b is the slit difference. N is the order number. How far away from the central spot are you? You know, first, second, third. Lambda is the wavelength of light coming from this exact same triangle pulled out there. Then we can simply draw in the exact same triangle we had earlier. It's just now h is only going up. This is to the first order minima, but we could come up to the second order minima or wherever we would like. The exact same triangle resulting here in the center. This theta is the same as that theta whenever your distance d is much, much greater than b, the slit width between, which the idea here is the slit width is very, very small. I should mention these pictures that I'm drawing are not to scale. This screen would be much, much, much further away, way, way off your computer screen or your phone screen right now watching this video. But whenever I do that, I've got tangent theta equals h over d, making the small angle approximation again. I can drop the tangent off, making sure that my angles aren't too large. Right, and I end up with h over d again, and so the exact same process. I can easily measure h, I can easily measure d, which allows me to work backwards. If I know b, then I can solve for my wavelength at that point in time, measuring h up to, let's say, the first order minima. I should also mention that if you knew the wavelength of light and you were trying to calculate the distance between the slits, you could do that easily measuring h and d and then working backwards to solve for b. Now, what does this all look like inside of a problem itself? So let me solve one for you. I have monochromatic coherent light, unknown wavelength. I'm going to end up solving for the wavelength. Passes through two small slits that are separated by 92 micrometers times 10 to the negative 6th. A second order maxima is found 5.3 centimeters above the central maxima on a screen 6.5 meters away. What's the wavelength of light? Now drawing in what I actually have here, right, I've got some angle, theta, going up to the second order maxima, 5.3 centimeters up. Never mind me drawing it to the first order maxima there. 5.3 centimeters up to the second order maxima. Here's the second order. Right up there, here's your 0, here's your first, right, counting up. And I'm looking for the wavelength of light. Now here I have my right triangle. I just simply use my tangent equals opposite over adjacent, but remember the tangent part dropped off because of the small angle, so theta equals h over d, so theta is going to equal centimeters, so 0.053 times 10 to the negative second, divided by 6.5 meters. And I come out with that angle is going to be 0.00815 radians. Now I'm going to substitute that into my constructive interference equation. That is, sine drops off because of the small angle approximation. Theta equals n lambda over b, and I know b here, and now I know theta. So this is getting substituted up here. I'm picking the constructive because I'm dealing with maximas, not minimas. Minimas would be dark spots, like in between. For example, that would be a second order minima here. So 0.00815 equals, this is the second order maxima times my wavelength, what I'm looking for, divided by b. Micrometers, let me make that equal sign a little bit clearer. 92 micrometers times 10 to the negative 6. Now I just solve for wavelength. And I come out with light 375 nanometers, 3.75 times 10 to the negative 7th. Nano means times 10 to the negative 9th, so jumping at 2 more places, I can call that nanometers there. Also notice my angle was well within the small angle approximation limits there, so everything works out quite nicely, and I'm able to calculate very accurately the wavelength of light from 2 nice, easy measurements that can be taken with just a meter stick. Now, I know this concept can seem somewhat confusing. We're going to continue to unpack it in class tomorrow, so make sure that you get good notes on this, rewatch parts if you need to, and come to class ready to go ahead and unpack this and then start into a lab pretty quickly.